Okay, thank you very much for this introduction. So indeed, we'll go over some of the work that we've been done in the clinic and in research on SGRT in Leuven. So this is where I come from. This is our health campus in Leuven. A lot of people work there, over 10,000 people we employ. Radiation oncology is right in the middle. You can see the arrow. And we treat, to give you an idea, 2,800 patients per year. So we have 3 C-arm linear accelerator, 2 O-ring linear accelerator, and also a proton therapy system. And all of these systems have been equipped with SGRT. We also have a dedicated team for SGRT, for surface guidance. A team of volunteers from the RTTs, really enthusiastic people who received additional training, and they import patients in alignRT. They are the primary point of contact. And then we also have a medical physics group that does more the development, the quality assurance of the devices. To give you an idea on the introduction of SGRT in Leuven, so we started 2018 with the first system installed on a TrueBeam system. And then we gradually moved towards implementing deep inspiration breath hold based on surface scanning. And then at some point, in September 2022, we hit the 50% mark, where half of our patients were treated with some kind of SGRT technique. Where are we today? Today we are somewhere at 75%, and it's still growing of patients that where we use SGRT during their treatment. So SGRT, protons, photons, we have O-ring system, C-arm system, and you'll see there's a difference. And we use different applications of SGRT, patient setup, monitoring, and gating deep inspiration breath hold. We also use them on the TrueBeam. And also in proton therapy and on our IBA Proteus 1, we have these techniques in place. And however, they're much more in an investigational phase for protons. So let's have a look at what we do on TrueBeam, or at least some history. So we started off in 2009 using deep inspiration breath hold based on the RPM, the Varian RPM system. And okay, it proved to be a good solution, but okay, there are some disadvantages. It is a surrogate, and so you see that. So in these EPIT images that are acquired during treatment, you see there is some residual motion present. What we also saw, because it's a surrogate, patients are trained and they have a feedback system, and they try to get the marker block in place. But sometimes they do certain things that they shouldn't do. For example, this back arching that brings the marker block in place. So from the RPM perspective, you are within the gate. But because of this back arching, that results in some anatomical changes where the breast itself or the thoracic wall is not in the right position because of its surrogacy. So that's something we detected, and that's why we were interested in using surface scanning for this purpose. And 2018, we moved to using SGRT for deep inspiration breath hold. So there we monitor the entire breast, and there we have a lot more information on the amplitude, but also on the breathing technique. But that's also important during this technique. And there we see, as you can see here, I don't know whether you can see the green line. It doesn't show very well on the projector, but maybe on the screens it does. And you see that, of course, with alignRT, we saw a much better agreement with the body contour during treatment planning. So that's already an improvement. What we did also saw was that we had to change the imaging protocol that we used for breasts because we wanted to acquire the surface together with the imaging. And for that purpose, we needed to use other angles for the imaging in order to be able to do them simultaneously, because in the standard way, the gantry head was blocking some of the view. So that's the impact it has. Deep inspiration breath hold with SGRT is done for left breast and chest wall. Lymphoma we started recently as well on Halcyon. And then setup and monitoring we do for a much more different sites, as you can see here. And I'll give you some examples on the last two, SBRT lung and intracranial SRS. So lung SBRT, tattoos versus alignRT setup, and we saw an improvement in setup. And that showed here, so an event overall, so the rotation in the longitudinal axis of the patient was reduced from 32% with tattoos to 12%. So that means that your setup is better, your workflow goes a lot smoother because you don't have to correct that much, and basically your patient spends less time on a treatment couch. So it's more efficient and more accurate. Another example is using SGRT during hyperarc. I don't know whether you're familiar with hyperarc, but it's a technique where you use multiple non-coplanar arc. It's a Varian solution on TrueBeam. It has a specific module for treatment planning that is dedicated to these brain irradiations. And it goes together with some kind of immobilization. So it's a total solution for these brain lesions. And it's very efficient, it goes very fast, and it's very automatic. But then again, it's non-coplanar. And in non-coplanar treatments, we know that KV imaging is usually very difficult or even impossible. So non-coplanar arcs, we use open face masks for these patients, and that allows us to use surface scanning. A cone-beam CT is acquired for image guidance in the beginning of treatment, and then we capture a reference surface. And during the delivery of the technique, which is fully automatic, no X-ray imaging is used, and we only rely on SGRT for verification of the patient setup during these couch rotations. And that's what you see here. So even prior to applying the mask, we use SGRT to set up the patient. We do that for a lot of cases. And then we verify couch rotations based on SGRT. And that's in the version that we have right now. It's fully automatic. So there's an integration between the TrueBeam and the Vision RT, the alignRT software, that it transfers the expected angle. And in this way, it can be monitored and verified that the patient is in the right position without any X-ray imaging. Now you see there are some spikes, but that's due to the fact that the synchronization is not optimal, so it can expect another angle, but at some point it knows, and it only goes about a few milliseconds there. So that's what we do in conventional linear accelerators with SGRT. There's also the O-ring devices. And SGRT and O-ring devices, that's an ongoing story. And it was not straightforward from the beginning. And I'll show you some history on that. So here you see my team back in 2017 as some happy faces, because we started off with Halcyon with the first treatment. So big smiles. But what you also see in this picture is that already in 2017 we had these Vision RT cameras mounted to the ceiling. So from the beginning, we believed in the combination of SGRT and Halcyon for a number of reasons. First of all, where do you put these cameras? Because we're used to C-arm, a more open structure of a linear accelerator, while now it's like a closed bore system. Where do you put these cameras? What's the optimal position of these cameras? If you look at a Halcyon system, so the isocenter is marked here in red, so it's inside the system. And a difficulty with that position is that in isocenter, you do not have access to the patient. So the RTTs, if they have to move the patient a little, or there's a little roll or whatever, or the arm is not right, arms might not be a big issue, but some other rotations, you basically don't have access inside the board to the patient. And that makes it really difficult. You have another isocenter, the setup isocenter, which is about 60 centimeters in front of the system, or at least in front of the isocenter, the actual isocenter. And there you do the setup of the patient and then move the patient inside the system. And there you have access to the patient to change the position if needed. So what we did in Leuven is to verify, or at least investigate, whether we could see the patient with the cameras. So we developed a ray tracing algorithm that could, in a way, anticipate or predict the coverage of these surface scanning cameras. And what you see here is that for the setup isocenter, so that's the 160 centimeters out of the bore, you could say, that you have quite coverage for this breast patient. So this is data acquired from patients. You have quite good coverage for the breast, but for the arms, for example, you only have visibility with one of the cameras. And we know that position of the arms is really important in breast irradiation. So already some limitations. If you look at the treatment isocenter, then, basically the two cameras on the side, because usually there are three cameras, they don't pick up anything because the gantry blocks the view. The one in front, there you can see something, but it's fairly limited, as you can see. So it's some parts are not covered. So it's problematic to do that with a ceiling-mounted device. You could bring it low enough, but then you might bump into it all the time, moving the patient or at least manipulating the patient, and that's also not very handy. So our workflow is step one, set up the patient at this setup isocenter, and then move in the patient, applying also the delta count, so a shift between the setup point and the actual isocenter. And we do that based on a setup plan without the delta, and then moving it into the bore and opening up the clinical treatment plan. So streamlining Halcyon. Halcyon is a very fast device in the sense that it's really an efficient workflow, but one of the requirements for that is that the patient setup is correct, because otherwise you run into issues. You don't have a 6D couch, so that means you bring it into the bore, and then if based on imaging, co-beam CT, you see that the patient is not correctly positioned, then you have to go back in and manipulate the patient, put him in the right position, and then you lose a lot of time. So in this case, if your initial setup is correct, then you are much more efficient. Now, this opened the question towards, can we do something else with SGRT? Can we look inside the bore? So we developed our own SGRT system based on, for the gamers among you, the Kinect. It's not sold anymore, but it used to be a camera that kind of picked up your motions and you could interact with the game. But these cameras basically have the same technology, structured light surface scanning as Vision RT. That's a similar technology. So we used two of those cameras to build our own SGRT system, which we could then position much better to have a better coverage inside the bore. We validated that, and it proved to be a good system. And based on that, we start monitoring patient. Obviously, we cannot use it for triggering or for actually using that signal for improving of the treatment. But at least we could monitor the patient and see what goes on. And then right away we see that it's a signal of high quality. So you see the breathing motion here. You see also baseline drifts. And you see here, for example, the couch shift applied after co-beam CT imaging. So from these signals, we saw that this is really interesting data and we can do something with it. We couldn't do at that point, any deep inspiration breath holds triggered based on our own device, but we could use the spirometer from Dinar. And so we did a study where we used that system, which was CE approved at the moment, to drive the treatment and then monitor with our own home-built SGRT system. This is what it looks like. So we use a two-camera setup behind at the back of the system, positioned in such a way that we had optimal coverage from that point. And what we saw was really interesting. So our deep inspiration breath hold treatments based on VMAT SIB were proved to be highly efficient. And we knew that Halcyon had the potential of doing that. and our median treatment time was 7 minutes and 36 seconds, including co-beam CT, image guidance, and 3 VMAT arcs, which is very good in my opinion. 92% of the fractions were done in 4 breath holds. You see 4 components, co-beam CT and 3 arcs, which means 1 breath hold for each component. And this was done in a population aged over 70, which is usually not the best population for these kind of breath hold situations. And this is the signal we get during these treatments. So you see baseline drift, so a lot of information comes in, and you see a CBCT-based correction. What you also see is that, okay, the signal that comes back from the spirometer, as there's no airflow during breath hold, obviously, is completely flat, while based on the information coming back from the SGRT system, you see that there is something happening during treatment. So you see gradually that for one patient more than another, but during this breath hold, patients are moving, and that's interesting information. And you can also monitor the amplitude of the breath hold, which is not something, well, you cannot do it with the spirometer signal, obviously. So you see a lot of additional information is available, which is great, but also opens a possibility, or at least the question whether it would be better to use that device for the triggering. So here you see some signals that we acquired. So on the top, an excellent fraction, very fast, the 4 breath holds and done. Then you see major difficulties, and that can happen. We know that with deep inspiration breath hold, people are trained, but some people tend to have, well, some difficulties at some point, but we did some additional coaching and regained confidence from the patient to do that in 4 breath holds. So now we published that data, and that inspired some companies like VisionRT to develop a commercial system, and this intra-bore system was, released a few years ago. And we installed these devices as well, and we started a study, but at the moment this is standard practice for breast and lymphoma cases in Leuven in the Halcyon system. And you see excellent agreements based on a deep inspiration breath hold co-beam CT versus deep inspiration breath hold CT. And you also see for the fractions we captured with the EPIT the beam effect of the first monitor units delivered for the VMAT, and you see a very good agreement for each fraction that is really reproducible from day to day for these fractions. And we saw that we could even further improve the efficiency. From 7.5 minutes, we went down to less than 5.5 minutes for the complete delivery of treatment. That's related to the fact that, okay, the spirometer, well, it needs some fiddling around with mount pieces. It's something you apply on the patient itself, which is always more difficult than a surface scanning based system. And it was in COVID times, so we're really happy that we didn't have to apply anything to the patient and we can do everything remotely. So also in COVID times, we really appreciated the fact that we could do it with surface scanning. But you see another improvement in efficiency. Okay, that's what we're doing in photons. We have since 2020, we have a proton therapy system in place. We treated 150 patients up until today. We treat the standard indications in Leuven up until now, so that's base of skull, craniospinal. So a lot of children, over 60% that we treat are the Belgian children that need proton therapy. And here as well, we installed the VisionRT alignRT system. That was the first installation in combination with Proteus One. And okay, the standard nowadays for imaging is a lot of X-rays. Certainly for pediatrics, we want to go low on the co-beam CT imaging. So a lot of X-ray imaging, and also because there are very complex motions or movements, couch movements between fields, we always use X-rays to validate that. So the question is, can we use surface scanning for that? But it's yet another geometry. It's an asymmetric setup because of the gantry. And the range shifter, I will go in detail about that, also causes problems. So we validated it with the couch positions and saw that there was a good performance of the alignRT system because it's a new setup, so we had to validate it. So but it showed sub-millimeter and sub-degree accuracy. This is an example, so pediatric medulloblastoma case in the beginning, where we used the device primarily to set up the patient before applying the mask. For these small children, 2 years old and even younger, it's very hard to position them and apply a mask. Even in the mask, they can move a little bit, and it's very hard to do that because their shape is not that well defined as they are so young. So it proved to be very useful to improve the setup of the patient and then, of course, increase the efficiency of treatment. And because these patients are most of the time under anesthesia, it's really important. Craniospinal radiations, it's a large group of what we treat in Belgium. It's a very complicated treatment. We do it with protons because there's a huge gain in exposure of a lot of vital organs with protons compared to VMAT and IMRT. We have a compact gantry system, which means that our field size in protons is only 20 by 24, so we need a lot of fields to cover that. So it becomes a very complicated treatment because you have to have different isocenters that all need to be verified. So that's what we're investigating at the moment, to use SGRT in that way, so we can, for the different parts of the treatment, use SGRT to verify the position of the patient and to monitor the position of the patient. The range shifter, I already mentioned that. So for the people among you familiar with proton therapy, so usually the energy goes down to 70 MeV. That's the lowest energy you get out of the gantry, and that means a range of about 4 centimeters. So if you have a lesion that is more superficial, you need an additional block of material, a so-called range shifter of 4 centimeters water equivalent thickness, that brings your Bragg peak all the way to the surface. Now that device needs to be as close as possible to the patient because it creates scatter and it widens the spot of your proton beam, so that reduces the definition of your or the resolution in a way of your treatment. So you want to avoid that and get the block as close as possible to the patient. But you can see that interferes with surface scanning because that means you also don't have access to the surface with the cameras. So that's problematic. So we saw for a posterior beam that the distance had to be at least 22 centimeters to get a good view on the patient to do SGRT. Now, okay, the setup is what it is, and it has its limitations, but we wanted to think about new solutions, other solutions. What can we improve? What is the impact? But one of the questions was maybe we should add more cameras or cameras in different places. So we had the 3 cameras already mounted, and we added virtually in a simulation environment 2 additional cameras very close to the isocenter on the X-ray imaging system that is present in a Proteus 1. And maybe the technology that they use with the small cameras in the intrabore on Halcyon could be applied here as well. That was our guess. And then we did a study where we virtually added these 2 cameras to have a 5-camera system that is more optimized for that environment. And then we made treatment plans that were optimized, which means that, okay, for each field in proton therapy, we optimized the air gap, made it as small as possible, but still allowing SGRT to be used for patient setup and monitoring. We did that for the 5-camera system and for the 3-camera system, the standard one. And then we compared with, well, the standard methods where we basically reduce the air gap maximally to like something like 7 centimeters, where you cannot use, or there's only limited use of SGRT, just to look at plan quality. And what did we see? That indeed, of course, the air gap is increased, which means that your plan quality is reduced. But we did see that with the 5-camera system, you could reduce that gap and almost bring the plan quality back to where it was without SGRT, or with the smallest air gap. Not all the way, but almost. Which means there is indeed a possibility to improve your treatment plan quality, reducing the air gap with in combination with the use of SGRT. That was the outcome of this study.
Tom, could you please conclude, because we are running out of time?
Okay, but I only have a few slides, so that's great. Also, motion management, we intend to use it. Motion management in SGRT is also difficult in the way that you need specific phantoms to do it. So we developed this breast phantom to do so, a moving breast phantom where we could have a moving surface that is more or less anthropomorphic. And here as well, we're doing studies to anticipate motion management treatments based on surface scanning in proton therapy. And okay, it's still work in progress, but I show you that, okay, these dosimetric results are already quite nice. We will further improve them in the future. But that's our goal, to also use SGRT in protons for example, deep inspiration breath hold. So this was an overview of what we're doing in Leuven with SGRT, both clinically and also some research. Just some concluding remarks. So SGRT has become a standard technique in use at Leuven. I think that's clear. More accurate setup, gaining more efficiency in workflows. We use it in a broad range of applications: setup, respiratory motion management, monitoring, both in protons on different gantries, in photons as well. Further improvements are possible to optimize performance in different gantry types, maybe with different camera systems. I don't know, it's a suggestion to the vendors. And there is added value definitely also in upcoming techniques. For example, online adaptive, if you're able in an ETOS system, for example, to monitor the patient during the online adaptation process, I think that's a big added value. Flash is going to be something that is upcoming. Very fast delivery of treatment, so you need to monitor the device and have a monitoring device with a very high refresh rate to monitor the patient and make sure that the patient is in the right position before you actually perform treatment. All right, and with that, I would like to thank you for your kind attention.